Okay, so now we're talking about Green's theorem. For the double integral of the curl will give us the line integral. When we talked about the curl, we mentioned that the curl basically measures at any individual point how much its tendency to rotate. So I'm not going to do a formal proof of Green's theorem, but basically what's happening is you take the region R, we'll call this R, that's in this path that's going around it, we'll say is counterclockwise. This is what we call a positive orientation. What you do, the way this works is you take this region and you break it up into a bunch of little rectangular pieces. And what you're doing is you're measuring the circulation on each of those little pieces. And that's basically what the curl does. It looks at the circulation at an individual point. Now, here's where this is cool, and this is why it works for a line integral. Now, remember, all of these are going clockwise. So if I expand on one of these, actually two of them, let's do two of them side by side. Right now, what's happening is, on this guy, we're going counterclockwise. And on this guy, we're going counterclockwise. But look what happens when I get here. These are in the opposite direction. So what happens is these cancel out. So what happens is on all these little paths, all the common sides, both horizontal and vertical, they all end up canceling each other out. And what we get left with is the circulation around the outside. Again, not a formal proof, but just give you a little bit of an intuitive idea of why these two are equal. And the proof uses that idea if you ever decide to look at it. What we need to take for us is that if we have a closed path, we may want to use Green's theorem instead of doing parameterization. Now, like we talked about last time, if we have a conservative vector field, we want to use the fundamental theorem. We're going to find a potential function and use the fundamental theorem. But for non-conservative vector fields, we either have to do parameterization unless it's a candidate for Green's theorem. Another thing that I'll mention for Green's theorem, we won't do anything like this in here. Let's say that our path is not closed. Maybe it's just this part of the quarter circle. What we can do is we can actually make it be closed. So we could also pretend like we're going to calculate the line integral in that path, for instance, or we could keep going around, whatever's easiest. Now it would be closed. So Green's theorem could be used on this region. Remember, our path is just this part here. So is just C. We're actually adding the purple parts in to make it closed. So Green's theorem could now be used. And then what we would do is we would just do the individual line integrals on these two parts and subtract them out. Okay? So it doesn't absolutely have to be closed in order to use it, because we could make it closed. Now, we'd only do that if making it closed makes it a nice, easy to deal with region. We don't want to make things harder for ourselves. So if that's something that makes our region easier to deal with, we'll close it, and then we'll just do line integrals on the purple paths and subtract those out from the total. The other thing I want to mention is if your region is not going counterclockwise. Okay, so if it is going, oops, sorry, that's already counterclockwise. If it's going clockwise, okay? Well, Green's theorem says it's supposed to be going counterclockwise. Well, because what we're measuring is circulation, if we did Green's theorem on a closed path that's going clockwise, the only thing that would come out incorrect in our answer is the sign, not the magnitude. So we could still use Green's theorem, and then we would just flip the sign at the end. All right, so while we want it to be closed and we want it to be going counterclockwise, those aren't absolutely necessary to use Green's theorem, but they're things that we would have to make adjustments for. Okay. All right. So let's do an example. Sometimes you'll hear this called circulation curl form, and I'll talk a little bit about the notations at the very end. All right, now this example was on the worksheet from last time, but we didn't do it in class. I did make a video doing it via parameterization. So what I'll do is after class today, I'm going to send out that video so you can see what it's like to do this, this line integral with parameterization. See that you get the same answer we're about to get, and see how it's done via parameterization. And you can decide for yourself which way you like better. So first thing I'm going to do is I'm going to rewrite our vector field in the form that I kind of like, which is with the brackets. So x, y, and instead of writing negative the quantity x minus y, I'm going to distribute that negative through, and we'll do just y minus x for our j component. So these are the same vector field. They just look a little different. And our path is a triangle connecting negative 1, 0, 1, 0, and 0, 1. And we're going to go in the counterclockwise direction. Again, if we weren't, let's change colors to make that a little more obvious. Again, if we weren't going in the counterclockwise direction, not a big deal. That's not a deal breaker by any means. We just know that we're going to have to change the sign because of the way Green's theorem is derived, it automatically does the counterclockwise direction. But this one's in the counterclockwise direction. So that's our path C. And inside there, that's our region R. All right, so let's go to work on this one. Now, if we were doing it via parameterization, which, like I said, I'll send you the video for it, you would parameterize each path on here. So if you're doing it via parameterization, you'd do maybe let's make that a little nicer. You'd make it into like maybe a C1, a C2, a C3, and just do 3 separate line integrals and then add up the total. And that's what I do in the video I'll send you. But let's talk about doing it with Green's theorem. The very first thing you do, calculate the curl of f. Guys, this should always be your first step because remember, if we get a curl equal to 0, we know that we have a conservative vector field and we'll just find a potential function. Now, as a reminder, the curl, which, this isn't something you have to memorize. This is something you could have on your note cards, is df2 dx minus df derivative of f1 dy, where again, we're calling this guy f1 and this guy f2. And as I'm going through this, guys, as always, if you have questions, feel free to turn on your mic and ask or post in chat, whatever's easiest. We've got practice calculating the curl. We did that last week. So we're going to take the derivative of f2 with respect to x, this will be 0, this will be negative 1. And then df1 with respect to y. So the derivative of this guy with respect to y is x, so minus x. It's not equal to 0. So it's not a vector field. We're not going to bother finding a potential function. But here's where we are so far. We're trying to calculate f dot dr. Remember that this notation means a line integral over our path C. Well, we're using Green's theorem. So a double integral over the region R of negative 1 minus x. And right now we'll just put dA because we haven't decided a direction yet. All right. That's basically all we're going to have left to do. Let me get these guys out of the way. All right. Now, at this point, Once you've decided to use Green's theorem and calculated the curl, you're back into module 4 mode. We set up our limits just like we would for any double integral, and we go to work. So I need equations for these lines. Well, the line at the bottom is pretty easy. It's just the x-axis, so that'd be y equals 0. This line has a slope of 1 and a y-intercept of 1. Let's put that point up there. That's 0.01. So that line's going to be y equals x plus 1. This one has a slope of -1 and a y-intercept of 1. So this is y equals 1 minus x. Now, again, we're back into module 4 mode. We have to decide which way is going to be easier, doing horizontal then vertical or vertical then horizontal. Notice if I were to do vertical first, in other words, if I were to integrate with respect to y first, well, my top and bottom is different on this side of the triangle than it is on this side of the triangle. So if we were to do top and bottom first, we would have to split this into 2 integrals. That's not a bad thing. It just means we'd have to calculate 2 integrals. We could do from 0 to x plus 1, and then -1 to 0, and 0 to 1 minus x, and then 0 to 1, and that'd be fine. But we would have to do 2 separate double integrals. So let's see if we can do it in one, because we have a definite single left and a definite single right. But that means we're going to integrate with respect to x first. So we do have to find the inverse of our functions. Basically means we just have to solve for x. So x equals 1 minus y for this one. And if we solve this one for x, x equals, x equals y minus 1 for that first one, sorry. So x equals y minus 1. Sorry, we just subtract the 1 over. Here, add the x, subtract the y, and this one's going to be x equals 1 minus y. These are going to give us our limits. So we can see that x is going to go from y minus 1 to 1 minus y. And then y is going to go from 0 up to 1. And we have -1 minus x, and now we're doing x first, and then y. So we now have our definite integral set up. Questions about that?
What would be the way that we would do this if we did not use Green's theorem?
You would parameterize each segment of the triangle. Like that's why I had the C1, C2, C3.
Oh, this is line integrals, huh?
Yes,
okay.
yes.
Because this is just like integrating that plane, and I was like confused because I was like, isn't this just regular integration? But it's line integrals.
Right.
Okay, that's why it's different. Got it.
I'm glad you bring that up. It's a good distinction, right?
So it looks the same except for the curl part. I'm like, this is how we do the integral of the plane between those points.
It's exactly the same.
Yeah.
And the curl is the function we integrate over.
Yeah.
You're exactly right.
Cool. All right.
Yeah, I'm glad you bring that up. It's a good distinction because just for a second, let's think about what's going on. For our line integral, it was a single integral of a single variable because we were parameterizing our curve in terms of a single variable. But with Green's theorem, as Cooper was mentioning, what we're doing is we're now integrating over a region in the xy plane. So now it's a double integral to integrate over the region. And with the curl being our integrand, what it's doing is it's actually giving us the circulation around the end, which is the line integral through the vector field. Other questions? Let's go ahead and solve this one because we have the time. But also, I want you to see the answer because I'm going to bring over the plot and we're going to take a look at it. So we're got 0, 1, integrate with respect to x, so minus x squared over 2. And this is going from y minus 1 to 1 minus y. And we'll still have to integrate with respect to y. So let's plug in those limits. It's going to look ugly at first, but it actually simplifies pretty nice because of the symmetry. So we're plugging in our upper limit for x. So 1 minus y is going in for those two x's. So let's put some brackets so you can see where they're going in. Minus 1 minus y squared over 2. So that's plugging in the upper limit, minus now our lower limit. So negative, now y minus 1 is going in. So y minus 1 minus, and then 1 minus y squared. So upper, lower, y minus 1. Sorry, I got that backwards again. I am backwards today for some reason. Apologies. Y minus 1 squared over 2. Didn't really leave myself much room for my dy there at the end. All right, now I'm going to do a little bit of simplification. Let me know if you got any questions on this. Well, basically, we just have to do, distribute this negative here. So in the first set of brackets, that's going to become minus 1 plus y. I'm going to leave this as minus 1 minus y squared over 2 for right now. You'll see why very quickly. Minus, now in these brackets, let's distribute this negative. So that's going to make a negative y plus 1, and then minus y minus 1 squared over 2 dy. Now, this is going to be pretty neat what happens simplification-wise. Notice I've got a negative 1 minus y squared over 2. And here I've got a y minus 1 squared over 2. Well, because this is squared, I can actually, it doesn't matter, I can write this as y minus 1 or 1 minus y. So we're going to rewrite that as 1 minus y, because it's the same thing. 1 minus y squared equals y minus 1 squared. Now, one thing I don't want you to do, 1 minus y squared is not 1 squared minus y squared. If you're going to multiply this out, you do have to FOIL it. But let's make a little note in there. What we did, if you go to look at this later, 1 minus y, the quantity squared, equals y minus 1, the quantity squared. And if you're wondering why, well, you factor in negative 1 out of y minus 1. That makes it 1 minus y, but negative 1 squared is 1. Or you can multiply it out, and you'll see that they come out the same. Now, the reason that that's useful is when we distribute this negative sign, look at what's going to happen. It's going to make that a positive. It's going to make this one a negative. And then it's going to make this one a positive. So what we see is we have a negative 1 and a negative 1. Sorry for changing colors like that, but that's going to make a negative 2. We have a positive y and a positive y, so plus 2y. But look at what happens here. Negative 1 minus y, the quantity squared over 2, and a positive 1 minus y squared over 2. Those actually cancel, and there is what we have left. So just to finish this one off, we get minus 2y plus y squared from 0 to 1. Plugging in the 1, we get negative 2 plus 1, or negative 1. So, again, that's just the algebra in it. But I want to show you what's going on. Notice we got a negative. So let me bring over the plot. So here it is in our Calc Plot 3D. And so if we see what's going on, and I talk about this in the parameterization video too, along this part of our curve, notice that the vector field is perpendicular. Well, if the vector field's perpendicular, then our line integral is 0. Remember, if it's in the direction of our path of motion, it's positive. If it's against, it's negative. If it's perpendicular, it's 0. So you pretty much get a 0 line integral along this path here. Now here, remember we're moving counterclockwise, so we're going in this direction, in this positive orientation. It's hard to see that line, so let me make it a little longer so you guys can see it. Let's extend the lines. They're scaled down. See how that vector is going against our path of motion? So we're getting a small negative value as we go up this part of our path because we're going against the vector field slightly. Now, as we come across here, now our vector field has larger magnitude and we're actually going against it again. So you'll see in the parameterization video, the line integral across the bottom is 0. On this path, it's -1/6, and on this path, it's -5/6, which corresponds with what we're seeing from the vector field. Questions at this point? Guys, that's Green's theorem. What's nice about it is because of our experience, think about it. You've already found, you know how to find the curl. We did that last week. You know how to set up a double integral for regions in the plane. We did that in module 4. Green's theorem is just combining those two ideas. Excuse me. Okay. We've already talked about the curl test, right? If the curl is 0, then we have a gradient field. So if we were to do Green's theorem, well, remember Green's theorem, it needs C to be a closed curve, then we're going to get 0. So if we get a 0 for the curl, we're not even going to use Green's theorem. We're going to go ahead and say, hey, we got a vector field. We're going to find the potential function. Now, if we get 0 for the curl and it's a closed path, we know it's 0 because remember you're ending where you started, and in a conservative vector field, if you end where you started, then the line integral is 0. All right, let's do the flux form of Green's theorem. So this is what's called a flux integral. All right, what's happening now is instead of taking the piece that is tangential to our motion, we're taking the piece that is normal to our motion or perpendicular. So we're going to do the double integral of the divergence instead of the curl. Again, we saw the divergence last time. This is the 2D version of the divergence theorem. A week from Tuesday, we'll talk about the divergence theorem in 3D. Basically, this measures the flow of the vector field across our path. That's what we call flux. That's a definition from physics. So we're integrating the perpendicular parts of the vector field where Green's theorem integrated the tangential parts. Now, what we're going to look at, remember we're going to do this exact same example. And what we're going to look at is now how much does our vector field go out of our region versus come in? Well, look at our vector field. We have more vectors pointing out of our region than we do pointing in. So we're going to expect this flux to be positive. But let's see what we get. We're going to do the exact same vector field, the exact same region. All we got to do is do the divergence. So what I'm going to do is I'm actually going to use a different whiteboard because here's what's nice. We've already done a good portion of the work. So first thing we do now, we've got the same vector field. So the first thing we do is, let's do a different color, is find the divergence of F. The divergence, there's nothing crazy going on with the divergence. You take df1 dx plus df2 dy. So the derivative of f1 with respect to x is y. The derivative of f2 with respect to y is 1. So y plus 1 is now our integrand. So we're going
Can you go to the, sorry, real quick. Can you go to the last page for me?
Sorry, what you need, Cooper?
Can you go to the last page? I didn't take down the
This page here?
The formula.
Okay.
Oh,
And
is there no
go ahead.
There's no actual numbers or anything like that.
Oh no, I'm using the same one from here.
Oh, okay. I'm sorry.
Sorry, yeah. I'm using the exact same example, except we're now doing the flux instead of the line integral. That's all.
Okay.
Same
Cool.
vector field, same region.
Okay. So you'd say you took the derivative of f1 with respect to x plus the derivative of f2 with respect to y.
With respect to y, yep. So this was
Isn't
f1.
the derivative of f2 with respect to y going to be negative x?
Well, remember, x is a constant with respect to y.
Oh, it's not multiplied by it. Gotcha.
Right.
Awesome. Thank you.
Yep.
That's
no
why
problem.
I was confused. I was like, there must be a different thing that I missed.
Nope, you got it. You're on
Thanks.
top of it. Yeah. Any other questions before we keep going? You know, this is going to be our integrand. All right, here's what's nice. Guys, our region's the same as before, so our limits are the same as before. We don't have to recalculate them. We already know we're going to go 0 to 1 in y, and y minus 1 to 1 minus y in x. Our integrand is y plus 1, and we're going dx dy. There's our integral. You know, if all we need to do is get to the answer, we can pop that in Simbo Lab and we've got our flux. Let's go ahead. We're expecting this to come out positive, so let's verify that. Now remember, we're integrating with respect to x first, which makes y plus 1 a constant. Here's a cool way to do this. Think of y plus 1 as its own quantity. Then the antiderivative is y plus 1 times x. Now I can put an x on each of these, but then I got to plug my limits in twice. So now I only got to plug my limits in at one place. And we'll see why that works out a little bit nicer here in the next step. All right, we got 0 to 1. We have y plus 1 out here. Now I'm going to plug in my limits. I'll use brackets to differentiate it. Upper limit is 1 minus y minus our lower limit, which is y minus 1 dy. So we got the integral from 0 to 1 of y plus 1. And then let's see what's going on in the brackets. We've got 1 minus y. Distribute that negative. We're going to have another negative y and another positive 1 dy. So basically, we're going to have to multiply those together. Y plus 1, and this is going to be 2 minus 2y dy. We'll FOIL that out, and then we'll do it piece by piece. So 0 to 1. We FOIL this out. We're going to get a minus 2y squared. We're going to have a plus 2y and a minus 2y. So let's go ahead and put those in, actually. Plus 2y minus 2y. Those will be nice and cancel out for us. And then we got a 1 times 2, so a plus 2 dy. Those cancel. After all is said and done, we have minus 2y squared plus 2 dy, and we're doing from 0 to 1. So minus 2/3 y cubed plus 2y from 0 to 1. The 0 is going to zero everything out, so we only have to plug in the 1. So we end up with minus 2/3 plus 2. So if we want to do this in thirds, we can say, okay, minus 2/3 plus 6/3 or 4/3, which is positive, which again, if we pull over our plot, we see more of the vector field going out of our region than coming in. So we were expecting a positive flux on this one. Questions about this one? Guys, I think you're going to find this section not bad because, again, this is all stuff you've done before. You've done double integrals. You've done curl. You've done divergence. It's just a matter of knowing which one to do when. And I want to show you some notation. So notation-wise, here's the notation that you're going to see. Circulation form of Green's theorem. Now, we've been doing the F.dr, which is also true. But here's another way of thinking of it. You're dotting the vector field with the tangential component of motion. You saw this form in the video, mdx plus mdy. And that's our double integral of the curl. So this is for line integrals. All right. Just the reason I'm really emphasizing the notation, you might see a problem that says, give me just a sec. I want to be able to annotate here. That basically says, find this. You need to know that this is saying find the line integral. All right. So that's telling you line integral. Again, I'm not expecting you to memorize it, but it might be something you want to put on your note card. Similarly, you see, either of these notations, this is what's telling you you're looking at a flux integral. The M and the N, those are just the components of our vector field. We could have easily put F1 and F2 in those spots, okay? This is just using some notation that's in the book. But again, I want you to be familiar with these notations. Again, I don't expect you to memorize them, but it can be confusing because, look, there's a plus here, but it's actually the curl, which uses a minus. This one, it's a minus, but it's the divergence, which uses a flux. Don't memorize it. Have it on your note card. Have your note card with you when you're going through the homework. You'll have your note card with you when you take the exam, okay? All right. You guys ready to try some, or are there any questions at this point? Let's do it. I like it. All right, so I'll split you up into groups. Let's see. We'll do two small groups. And if that doesn't work out, if you need a bigger group, you can let me know. Here's what I want you to work on from the worksheet. Number 2. Don't worry about number 1. You can always try those later, but for today, for this class period, number 2, there's an A and a B, and you're going to use both versions of Green's theorem for both A and B. Now remember, just like I did here, once you set up your region for, let's say you do the line integral first, once you set up your region of integration for your line integral, if you're doing the same vector field and the same path, it's the exact same setup here for your flux integral and vice versa. So yeah, there's 4 problems here, but you're using the same vector field and path on A and same vector field and path on B. And the reason I'm giving you both, I think A is a little bit easier, so that'll be kind of get a little bit used to the notation. And B, you got a little bit more interesting region where you have to find an equation and work with that, okay? So I want to give you a chance to try both. If you want to skip right to 2B, that's fine, and do that first, totally fine. So you guys can kind of decide what you think you want to work on. So basically work in pairs today. All right, so you should see the breakout rooms. Guys, call me in if you're having any issues, or if you finish early. If you might get through these quick. If you get through these quick, call me in or come back into the main room and we'll go on and do other stuff or end early or whatever we need to do. So you should see an invitation into the breakout room. Perfect. And you're fine where you're at, Cooper. I'll be probably in and out of the rooms, but I'll be here if you got any questions.